Hello, and welcome back to another video with It's Dr. Dan. And what are we going to be learning about today is matter. Specifically with how do we look at matter when it comes to chemistry. We are going to be going through this video from an introductory standpoint, just so you can get the fundamentals of how we look at things. So in this course, the big thing that we like to understand is we go from the ground up. And assuming that matter exists as particles, so the smallest type of pieces you can possibly imagine. So things like atoms, or even what even makes up atoms, are smaller. So when we look at particles, what exactly are we talking about? How small? Well, here I have a photo, as you can see, of someone spraying a mist. And we're talking on a really, really small scale. So if you think of this mist that's all here, and you think of the finest little droplets that are in here, we're kind of going to zoom on that, and we're looking at particles that are about that size and even smaller. So imagine that small, but another million or so times smaller than that. So as small as you can possibly go down to the atomic scale. So whenever we are looking at these things, we want to think of all these little specks, and the way that we're looking at these particles is that they're all spaced out, and that generally we just portray let's look at how we portray all these little different particles moving forward. So when we're looking at particles, the whole idea is that they are made up of atoms from your periodic table. Now, particle, I'm using that as a very generic term, just to refer to something that's really small. So in a lot of times when it comes to courses, we like to show these as very, very tiny atoms, and they're usually represented by little dots. So whenever we have those little dots, this is a way for us to really be able to imagine and see all the different atoms that are within a gas, or maybe a solid, or any type of material. Now, when it comes to molecules, well, usually you'll see these little dots and they're all stuck together. They're glued together, and meaning they are bonded. So we'll use this word chemical bonding very often from now on out. So you'll see the dots are connected. So what happens if these things are connected and they're close together? How can we look at these pictures? So first off is looking at the phases of matter. So matter comes in many different forms. So there's solids, liquids, gases, and also plasmas. But we're going to be focusing on those first three because they're what makes up most things that you will come across. So solids, usually you are going to be exposed to these around you. So these are typically in a very organized pattern, meaning that you'll commonly see them as a repeating pattern. And we like to say that these are crystalline as a result. So crystalline, as you can see, we have this pattern, right? Then we have 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, repeating. So many of these solids that we have all around us, whether even a lot of things that you have in front of you, have a specific crystalline structure. If you look at all different geodes and rocks, you actually see that many of them have all kinds of unique structures in them. In fact, if you look at sodium chloride or table salt that you have at home, it actually exists in a cubic shape on the atomic level if you were to zoom in on it with a very powerful microscope. Now, do all solids exist this way? And no, if you kind of think of things that are like rubber or they have an elastic character, these things are generally called amorphous because they are more disorderly and they just kind of flop on top of each other, but they're still tightly bound together. They have a very high density typically because of how close these are together. So solids have a very definite volume, and they have a definite shape behind it. And that's the important thing. It's a definite volume and shape. Versus liquids, liquids do not have a definite shape, but they do have a definite volume, meaning that the atoms are still very, very close together, and they more kind of slide and slither past each other. Solids are all nice and close and hunkered together, very nice and packed, where liquids are more go with the flow. They're more relaxed as a result. So these they will take the volume of whatever container they're in. So you think of a liquid, if I have a cup of water, right, it's going to take the shape of that cup. But if I were to dump the water onto the countertop, it's now the shape of your counter. Or if it falls onto the floor, it's now the shape of the floor. It just takes whatever thing holds it together. But you can measure the volume, right? You could take all that water, put it in a grad cylinder, measure it, and be able to see that it has a very exact volume. Now, when it comes to gases, they do not have a definite shape or a definite volume, meaning that you can compress them. Now, why is that exactly? And that's because atoms are like, or gas atoms are like little billiard balls that are free moving and they exist very, very far apart, meaning that between them, there's a ton of empty space between them. They move extremely fast. Generally has to do with the temperature that is behind them. So if they have a lot of kinetic energy within them, they will move very quickly. And if they have a lower temperature, they'll move very, very slowly. So typically you can try to describe these things as very fast moving most of the time. So I like to think of gas particles kind of like bouncing all over the place, like a 5-year-old hyped up on sugar at a birthday party, being that they are going so incredibly fast. So we have those 3 phases. How can we try to classify all the things around us, right? You can look around maybe your room or wherever it is that you're watching this video, and you can see many different forms of matter around you, whether it's your laptop, your phone, maybe your desk, maybe your chair, your clothing, all these things are different. So how can we classify matter? Well, the way that we do it in the scientific community is we do it by composition. What is it made up of? So there's 2 ways we can classify this. We can either classify them as a pure substance, meaning that it's only made up of one type of particle. One type meaning one atom or one specific compound. It could be one or the other. Mixtures are whenever we have essentially more than one type. So if you take, let's say if you had air, for example, air has oxygen, nitrogen, many other gases. That would be a mixture. Now, if you had, let's say, if you take like your salt shaker and there's only sodium chloride inside of it, that would be a pure substance. So it can exist in a couple different ways. Pure substances can be both elements and compounds, so it can be both. And then mixtures can be separated into 2 different forms as well, which are homogeneous and heterogeneous mixtures. Let's take a look at both so that way we can understand exactly what they mean and how we can understand what they are. So the first one, which was the elements and the pure substances. So these are when you have just one type of atom, meaning that it could be, if you take your periodic table, it could be any one of those different atoms that are there. Now, all atoms, they don't always necessarily exist by themselves, like this little top picture here. Sometimes they might be bound to themselves in different arrangements. However, they are still just one atom. So an example like this is something like O2, oxygen gas, right? You're breathing in O2 right now, but it's still one element, but they just happen to be connected. So it's a little different than a compound. Now, other ways that you can have these different elements all connect together is when you have things called allotropes. We really don't discuss them a lot in this class, but it's just kind of nice to know. So if you think of carbon, right? So if you burn something and that soot that's left behind, that's carbon. Now, if you put that under a lot of pressure, you could get coal, or you can get graphite, or if you put it under enough pressure and time, you can get diamonds. All of those are all carbon, right? And you look at a diamond versus coal, they look nothing alike, but it's all based on pressure and time. So these are all different versions of a pure element. Now, the most important pure elements for you to remember without just having your periodic table is realizing that whenever an element bonds to itself, and there's only 2 of those atoms bound together, so like O2, H2, N2, these are referred to as diatomics. So diatomic gases, there's 7 of them, so I refer to them as the diatomic 7. You need to memorize them for any chemistry course, or even any future higher level chem courses, even some if you're in respiratory therapy or any type of biology courses as well, they come up quite often. So these 7 types of gases, in order to remember them, there's hydrogen, nitrogen gas, fluorine, oxygen, iodine, chlorine, and bromine. Now, trying to remember all 7 of these diatomic gases can be a little tricky. So I have a mnemonic that I love to use, I found online, and it's have no fear of ice cold beer. So if you remember that, right, the first letter of each of these words represents one of these elements that are over here, and I color coded them to help match. So if you remember have no fear of ice cold beer, you will never forget your 7 diatomics. So H for have, so that'd be hydrogen, and N would be nitrogen, and so on. This will be very helpful for you. You need to memorize them for future courses. Now, these are your elements. Compounds are, just to talk about them, right? It's whenever you have 2 or more elements that are bound together, meaning they exist in a very fixed proportion. One example of this is water, right? You drink water every single day, hopefully, if you're taking care of yourself, but it always exists as 2 hydrogen atoms to every 1 oxygen atom. It's in a ratio. Now, this is a pure substance. If you have a clean glass of water and it went through a filter, you can drink it and it is only water. Now, if you have salt as well, so sodium chloride in that solution as well, well, now all of a sudden you have more of a mixture as a result, right? It could be soluble, it could be homogeneous, heterogeneous. You can classify that. But sodium chloride, NaCl, notice that when you have this crystal pattern, it's this repeating lattice, so crystalline structure, but this is a pure solid of only Na and Cl ions that are connected together. So you have that specific portion when you are looking at these. Now, compounds, they can also do all kinds of cool chemistry. You can break them apart and they decompose into completely different pieces. So you can see that. So that's what we're going to look at right now. Right. So what we're seeing here is someone's putting sugar in this container and they're dumping sulfuric acid onto the sugar. And immediately you notice the properties of these materials are immediately changing. The sugar, right, is normally a white crystalline solid. The sulfuric acid was this clear solution. Now all of a sudden you can see that the chemical properties are immediately changing. They're very reactive together, right? So they change to black. Now, if I unpause it, you're gonna start seeing that they're starting to bubble. If you look very, very closely right here, notice how there's bubbles forming. And if you mix it and give it a little bit of an agitation, you can see the sugar's dissolving and more bubbles are starting to form. It's gonna start turning darker and darker, and a lot of heat is going to be released. So meaning that the temperature is going to be changing, and therefore you're going to see this very thermodynamic process is occurring. So if I unpause it again, and this is happening in real time as well, you can see all of a sudden the volume is changing of this material. That's because you're creating something new. You're creating a new chemical. So the pure substance can dissolve and turn into something brand new. So what this pure compound or sugar is decomposing into is, you can see it's turning into pure elemental carbon. So this is all carbon that's coming out of this. So it's like a big carbon snake that's coming off. And you can see all of this gas that's completely evaporating off because of how hot this thing can be. So this is chemistry in action. It's really one of my favorites. But this thing's a big mess, so I don't know if we do it in the lab. The next part of our series is looking at mixtures. So there's homogeneous, which means homo meaning same, and then heterogeneous mixtures. So what this is all about is that when you have multiple pure compounds and they're all mixed together, this makes a mixture. So homogeneous is when you can't physically separate them. So you can't tell just by looking at it that there is a difference between them. They are uniform. So an example of this would be something like if you have like air or many other different types of mixtures, like all these solutions of nickel that I have up here. Notice how they're blue, they're purple, they're like a yellowy green, a teal. So all these are mixtures of nickel with water, and they all have completely different colors. You can see that's all completely uniform. And even if you zoom in on it on the atomic level, so just going off my little particle drawings, notice how all the areas are very uniform. There's no rough patches anywhere. It looks, you wouldn't, if you took one section from another, you wouldn't be able to tell the difference, right? So they're all the same. So homogeneous is like, think of air. It is one solid or one complete mixture. You can't pick out like the oxygen atoms from the nitrogen. If you tried picking out air in front of you, people are going to think you're crazy. Another homogeneous mixture would be like milk, for example, right? There's proteins in there, some fat, also water, but you can't see the different layers unless it goes bad, right? But if it's normal milk, it looks just like normal, right? But it's a mixture. Now with heterogeneous, this means that it's not uniform. So you can actually see that there are different, completely different pieces of it. So an easy example, think of a hot fudge sundae, right? You have the fudge, the caramel, nuts, sprinkles, all these different things on top of it. But if you wanted to, you could pick out all the different parts. You could separate them all out. So by like maybe melting the ice cream, like maybe filtering out different pieces, you can take all these little parts out. You're in the lab, you're going to see different heterogeneous mixtures. After a chemical reaction might occur, you might see a solid form in the glassware, and there's also the liquid water layer, but notice how they're separated from each other. So this is a mixture that is heterogeneous. Another example is think back to the density videos that I've shown before with all the different layers there are. Those are heterogeneous because you can easily see the different layers that exist. So that is one of the big things when we're trying to separate these. Look at all the little pieces that we have. Okay, so going forward, to distinguish between all the different properties, all the different pieces of matter and all their properties, is that we have physical and chemical properties. So these have been mentioned in previous videos, but just to quickly go over them, a physical property does not require the substance to change its identity. So one easy example is that I always like to use is, let's say if we had like something like, let's say a napkin, for example, and if I were to take that napkin and I were to rip it in half, right? So just tear it into pieces. Is it still technically a napkin? And one thing you could say is, it is, right? It's still a napkin, even if it's in shreds. I could rip it apart again and again and again, and I could have all these little pieces of the napkin, but it is still a napkin. Another way to look at a physical change is, let's say if you have, you get a glass of water and you have ice in it. Over time, the ice will melt into water, but the ice was always water all along. And heck, if you left your cup of ice on the counter, or your cup of water on the counter for, let's say, a week, all of a sudden all the water will have evaporated into water gas over time as well. It's still water. Chemical properties is whenever there's something that is completely changed, and it's generally due to the chemical reaction, because you are actually having the composition is changing. One of the ways that you could see that was when we had the sugar with sulfuric acid. It went through a chemical change because its property was that it could react with sulfuric acid. So all substances display physical and chemical properties. And the way that they display these is through physical and chemical changes. So we're always interested in how things are changing. So what kind of changes could we have looking forward is if you think of how something new can be created, right? You want to see that there's, you want to take those observations and measurements that we're going to be doing in the lab and record them. So if I were to look at, let's say, the different flames that are up here in the top right corner, what do you observe? Well, it's hot. You see colors, that light is being emitted. You can see that, if there are marshmallows lit on fire, you can see the color of them is changing in front of you, right? You can smell it. There is changes. If I look at this cup here, right, you see bubbles forming, meaning gases. are coming off it. If you touch the side of the container, maybe you'll see heat is coming off of it, right? There are evidence or observations of new changes versus, let's say, a physical change is just when you take something in, let's say you take a glass, right? And you have that glass in your hand, you smash it into 1,000 pieces. It's now just 1,000 pieces of glass. It's still the same thing. Phase changes, which we'll talk about in future videos as well, going from melting, freezing, boiling, evaporating, all of these are still the same substance. They're not going through a chemical reaction. They're just changing. So that's going to be what we're going to be seeing up in the upcoming weeks. So thank you so much for listening. This is the idea of the basics of matter, and I hope that you enjoyed it a little bit, and we will be seeing more in the future. Thank you so much for listening, and I'll see you all later.